cryptography tutorial. Now, cryptography is a very important field in the ethical hacking domain, so we're going to go over that today. But before we actually begin, be sure to hit that subscribe button and click on that bell notification icon so you don't miss out on any updates from us. So, let us get to the agenda without any further ado. So today we're going to be discussing the introduction to cryptography because before we get into any of the algorithms that cryptography entails, we need to understand what cryptography is in the first place. Then we're going to understand the categories of cryptography because there are several categories in which cryptography has been divided into. Then we're going to understand and look at some of the examples of cryptography because obviously we cannot look at all of the examples. There are a lot of cryptographic algorithms that are present in today's world. So we're going to look at some of those and look at how they work to get an idea of how this entire domain is actually functioning. And then finally, with respect to ethical hacking, we're going to understand cryptography hands-on. So we're going to be implementing some assignments actually on a live virtual environment where we're going to be implementing cryptographic algorithms on files. So with that said, let us actually begin. So firstly, introduction to cryptography. So, firstly, let us understand what the term cryptography actually means. So, cryptography is theoretically defined as the study of the various processes which are implemented to protect information and communications through the use of mathematical concepts and rule-based calculations. So, essentially, you have data. So this data could be a static message that you're trying to send to somebody. This data could also be a communication bit that you're actually trying to send to someone in a streaming format, right? So what will happen is if you want to protect that data, you pass it through some mathematical operations or rule-based calculations, and then that data becomes protected, right? So essentially, if somebody else were trying to actually access that data, they couldn't, right? So this is what cryptography is. It is the study of these processes that help achieve this. Now, the question comes up, why can't we simply send data to our desired recipient without actually having to implement this? So, let us understand that as well. So, why do we need cryptography in the first place? So, imagine that you're the sender of the message, you're the originator of the message, and you have a message, you have a data file, right? So, the blue icon over there represents the data file and there is a recipient, right? So you're sending this data to the recipient via the use of email, say for example, right? So you send that to your recipient. This is what happens if the message goes normally and nothing bad happens at all, right? But there's an off chance that there is an intruder that has access to the actual connection between you and the recipient, right? And your email line is essentially not secure, right? So this could be in the case when you're trying to send data over a local area network, right? And the local area network is compromised to give the intruder the access to all of the traffic that is present in that network, right? So you send this data file, it goes to the recipient, but it also goes to the intruder. Or worse, what could happen is it could go to the intruder first, the intruder could make some adjustments to it, and then it could go to the recipient, right? Either way, this is not something you want, right? So, how do you fix that? The intruder is able to read your data. uh, we need some method to make this data unreadable by the intruder. So this data that the intruder also gets access to, even though he has access to the email line, we need to do something with this file that makes it unreadable by the intruder. So we do this with encryption. So what is encryption exactly? Encryption or enciphering is a cryptographic process where we convert plain text, which means the text that we directly enter onto our keyboards or raw data, to unintelligible information or cipher. Right, so unintelligible information means random gibberish, or so it appears to somebody who looks at it from a third person's perspective, random data essentially, by processing the data with an algorithm, right? So you're the sender, right? And you have some data in the plain text format, right? What will happen is you'll convert that plain text data into a cipher by passing it through an algorithm or some sort of a processing framework, right? And once you've done that, you pass that cipher on to the recipient, right? So even if the intruder gets the access uh, between you and the recipient, the person will not be able to understand the original meaning of the message because it has been converted into something else. It has been converted into unintelligible information. And so, what is decryption essentially? Decryption or deciphering is a cryptographic process of converting the plain text, converting the cipher back into the plain text by processing the data with an algorithm. So once the cipher reaches the recipient over the email line, now the recipient needs to actually get the actual information that you're trying to send them, right? So they need to convert that cipher that you've sent them back to plain text. So this process is essentially called decryption or deciphering, right? So let us continue. There is another term that we need to familiarize ourselves with, which is quite prominent today. It's called cryptanalysis, right? So, cryptanalysis is the study of deciphering ciphers without knowledge of the encryption technique. So, earlier on, traditionally, decryption is done when the recipient's end knows how to actually decipher the cipher, right? They have a key or something, they have the algorithm to reverse engineer the cipher back into the plain text, right? So, cryptanalysis, on the other hand, is the study of deciphering ciphers when you don't have any prior knowledge of the encryption technique. So, you don't have any keys, you don't know the encryption technique, you don't know the reverse algorithm. So, cryptanalysis is the study when you try to convert ciphers by just looking at them and converting them back into plain text, right? So, that is called cryptanalysis. A cryptanalysis is what a hacker will do if he's trying to actually get information out of the cipher that he has access to. So there are some security goals that are involved in the process of cryptography. So we just go over them one by one. Confidentiality. So the first principle and the foremost principle, as we all can understand by now, is when you try to send data over an unsecure or secure line for that matter, and that data is only expected to be read by a particular amount of recipients or a particular recipient, you need to maintain confidentiality or secrecy with that, right? So in larger companies where data is sensitive, right, and data cannot be read by other people, data cannot be accessed by other people, or it could cause a massive blunder, right? So in that case, you need to absolutely protect the confidentiality of the data. So cryptography is the study that helps us deal with that. It helps us protect the confidentiality of the data. So the first principle that we actually deal with when we are implementing cryptography is confidentiality. The second is integrity. Now, integrity means that the data should have its original meaning, should have its original structure when it reaches the recipient. So if you write something in the beginning, right, and you convert it into cipher, when you send the cipher over to the recipient and the recipient deciphers it, converts it back into plain text, the plain text should represent exactly what the sender sent in the first place. So the data should have maintained its integrity. It should be whole, right? It should not have been manipulated by any attacker in between, or there should not have been any loss of the data in the encryption process itself. So this is another goal of cryptography, to maintain integrity in the data. And lastly, one of the other most important things is availability. Now, availability means that the people who require that data should have it basically instantly, right? They should not have any delay with getting that data. Nobody should be able to interrupt the process of them getting that data, right? So this particular aspect is called availability, which also means that the encryption techniques that we're using, the encryption and decryption techniques that we're using, should be fast in nature. So when it reaches the recipient should be able to decrypt that data fast, because time is extremely valuable, and the recipient cannot sit and decrypt that data for 1 to 2 hours. It should be decrypted in minutes if that is ideal, with the algorithms that are present to the recipient. Right. So these are the three security goals that we deal with when we're dealing with cryptography. So there are categories involved in cryptography essentially. So other than the examples that we're going to discuss after this, cryptography has been divided into particular categories. So let us look at that. So the fundamental categories are private key cryptography. Now, private key cryptography is also called symmetric key cryptography. It uses a single common key on the receiving and the sending end, right? So as a sender and the receiver, you use one key to encrypt and then use the same key to decrypt that data, right? So you're the sender, you have access to a key. Now this key is not shared with anybody at all except the recipients or the intended recipients, right? So this key is present to with the recipient. You have the data with yourself. You encrypt that data using that key, and you convert it into the cipher, and then you send that over to the recipient. Now the recipient has the cipher. The recipient will use the same exact key. Now this key is a private key. It has not been shared with anybody to decrypt that data, and that data is converted back into plain text. So even if an intruder accesses that cipher in between, since the intruder does not have access to this key, he will not be able to decrypt that data. Now this is called private key cryptography or symmetric key cryptography. Only one key is involved in the entire process. Now, on the other hand, we have public key cryptography. Now, public key cryptography is also called asymmetric key cryptography. Now, this exactly means that there are two keys that are involved. So, one is a publicly available key. Now, this key could be available to the intended recipients and senders, right? Or this key could be available to the world as well. It does not matter, right? So even if the public key is available to a lot of people who are not supposed to have that, it does not matter at all. So what happens is, in this particular case, the data is encrypted with this public key that may be available to a lot of people who are not supposed to have access to the data, right? With this public key, the only thing that you can do is encrypt this data, right? You cannot actually decrypt this data with the public key. You can only encrypt this data with that public key, right? So you basically go ahead and convert that data into cipher using that public key. You send that cipher over to the intended recipient. Now, the intended recipient has a private key. Now, the private key is only accessed by the intended recipients. Nobody else has access to the private keys. Everybody has access to the public keys. Nobody has access to the private keys. Now, what the recipient can do is decrypt that data with the private key and convert it back into the intended data or the plain text, right? So, the advantage of this is you don't have to keep access, you don't have to keep the public key secret at all. And even if the public key is available to everybody, uh, nobody can do anything with it. If an intruder gets access to the cipher in between the line of communication, he cannot use the public key to decrypt that data, because the public key has been used to encrypt that data, and the data is meant to be decrypted only by the intended private key, right? So This uses a non-secretive public key for encryption and a secret private key for decryption. Now, there are comparison points between the two. So, public key encryption and private key encryption, the differences. Firstly, in private key, obviously single key required. In public key, there are two keys that are required. In private key, size of the cipher text is less than equal to the plain text. In public key, the size of the cipher text is greater than equal to plain text. Private key cryptography has fast encryption, less resources. So with only a single key, you don't have to worry about a lot of processing power. Essentially, what happens is you can encrypt and decrypt your data extremely fast and use less computational resources, while in public key, there is slow encryption and the usage of high resources. Private key is generally used for large data because of the fast nature of the encryption and decryption processes. So if you have a large data, you will generally go with a symmetric key cryptography method. And for small data, you will go with public key cryptography methods. Now, there is confidentiality, which is absolutely maintained in private key cryptography, but with public key cryptography, although slow, you get confidentiality, authenticity, and non-repudiation. So in public key cryptography, the data has confidentiality, which means that the data is secretive in nature and will only be revealed to the intended parties. The data has authenticity, which means that it can be verifiable where this data came from. It cannot be coming from an attacker or an intruder. We verify that with means, and there is non-repudiation, which means that the receiving end cannot deny that the data is authentic and has integrity. So there are ways to check integrity of the data, like checksum and other methodologies. With the help of that, the receiving end cannot deny that the data is authentic. So examples of these in private key cryptography, we have 3DES, AES, DES, and RC4 algorithms. In public key cryptography, we have Diffie-Hellman, ECC, EI, Gamal, DSA, and RSA. There are also hash functions. So hash functions are pretty straightforward. I think the easiest to understand out of all of these algorithms. Functions that convert plain text into encrypted text are called hash functions. So essentially mathematical functions. So if you're aware of this, this is what it looks like. You have a function. Within that function, you pass in a variable called plain text, right? So this is your input, and then you get the output, which is the cipher, right? So functions work in exactly the same way as a lot of the other algorithms would work, except you have a lot of flexibility attached to them. You can essentially create any sort of function that you require for your particular use case. Let us look at the examples of cryptography now. So if we move on ahead and look at the easiest and the first example, so this is a sort of a substitution algorithm that we use for encryption and decryption. It's called Caesar cipher, right? So imagine you have the entire alphabetical list available to you from ABC to XYZ. You have all of these letters available to you, right? And say your message is fun. Now, this is the word that you're trying to send to your intended recipient, right? But you can't send that directly. You need to encrypt it, right? So, let us take a value n. N is equal to 3. Now, this could be anything. N could be anything at all. It does not really matter what n is. It is up to the encryption algorithm or the encryptor to decide what the value of n will be. Now, this is the only value that is required to be known by the recipient, the value of n. So imagine the letters that come three sides or the value of n to the right. So with f, we have 1, 2, 3, we have G, H, I. So for f, we have I. For n, we have Q. And for U, we have X. So you can also see in the alphabetical list, the letters have been marked with green, which are present three positions to the right of the intended letters. So what will happen is we essentially convert it to that. So for F, we get I, for U, we get X, and for N, we get Q, right? So this is what happens when we use the value of 3 to encrypt our sentence or word with Caesar cipher, right? So our final encrypted text is IXQ. So by shifting the position of each alphabet forward by 3, we are able to hide the original meaning of the word, right? This is called a substitution algorithm because we are essentially substituting the original letters, right? So F has been substituted by I, U by X, and N by Q, right? So this is one of the first and simple algorithms for cryptography, but it gets you going with the idea. Now, next up, we have another category and type of cryptography. An example would be the rail fence cipher, which is a transposition technique. Now, this is an interesting technique as well. Say you have a sentence that you want to encrypt before sending to your recipient. It's called hello from Intellipaat, right? And what you'll do now is you'll imagine you have two rail fences. Now you can implement this using programming languages, but I'll give you the basic rundown of how the algorithm works visually. You have two rail fences, similar to the boundaries that you have on your home. That is why it's called a rail fence, right? And what you'll do now is simply start writing the letters alternatively on these rail fences. So firstly, you have H, right? So H has been highlighted in the sentence and H has been put on the first rail fence. Then the next letter is E. So alternatively, you'll put this on the bottom rail fence. Now, we are using two rail fences right now. You can use as many as you want, but it's generally preferred that you go with one-fourth the size of the actual string that you have, so that there is actual implementation of the rail fence cipher instead of you actually making as many rail fences as there are letters in your sentence. Then what you'll do is write E on the bottom rail fence, and similar to that, you'll alternate to the top rail fence once again and write L, right? So on and so forth. You'll fill it in a similar fashion. So it'll look something like this, right? So what you will do now is you'll take the entire string that is present in the first rail fence, and then you'll append it to the string present in the second rail fence. And if you had multiple rail fences after that, you would have done the same thing with the consecutive rail fences as well. So now the final text will look something like this. It looks kind of like gibberish. Now, one thing you might be noticing is I haven't actually implemented the white spaces, so that is only for non-confusion purposes. You can implement spaces, but since we wouldn't have been able to see spaces over here to avoid any sort of complexity, I removed them. But you can definitely implement spaces as well when you're dealing with programming languages, right? So the final cipher text will look something like this, right? And this particular algorithm is called a transposition technique because you're not exactly substituting anything over here. The letters are the same as in the original string, but they just have been jumbled up, right? So this is since the position of the letters have been changed, this is called a transpositional technique. The original letters have not been changed, only the positions have been changed. So this is what a rail fence cipher is. The only thing that your intended recipient is supposed to know in this case is the number of rail fences, right? And in the previous algorithm, which we were discussing, which was the Caesar cipher, the only thing that the recipient needed to know was the value of n, right? As to how many letters you're shifting to the right or to the left. That is only required to be known by the recipient. So these particular techniques, the rail fence cipher and the Caesar cipher, are extremely weak techniques. With today's computational technology, they can be broken almost instantly. So these are not ciphers that are used in today's environment, although we use other ciphers. So let us look at one of the ciphers that we can actually use. In this case, this entire process is called steganography, and we'll look at an example of that. Firstly, let us understand what this actually means. Steganography is the technique of hiding secret data within ordinary, innocent-looking files and messages, right? So what happens is you have your data, right? And the way you will hide this particular data is you'll simply embed it within an image, right? So whenever somebody looks at the image file, they will not see the presence of any data. They will not even see a trace of the presence of any data unless they have the required tool required to decrypt that data from within that image, right? So this entire process is called steganography. This can be useful if you're trying to hide information on your computer system, or if you're trying to hide information within an email. So say there is something that has been talked about between you and the recipient on the phone. You both have the same steganography tool, right? And then you decide to send an ordinary image file over the email to your intended recipient, right? So even if somebody is able to access that mail in between the line of communication, they will just look at an image and they will think, okay, it's an innocent file. There's nothing to worry about over here, right? So this is the entire point of steganography. So let us look at how this works. So we're using a steganography tool. Now this tool, the only people who would have this tool are the senders and then the recipients, right? So this is a tool which essentially helps you hide or encrypt some data behind image files, right? So if any normal person tries to access that image, they will only see the image, while the people who have this tool can actually see the hidden message behind that image, right? So the first thing, obviously, that we would do is actually select an innocent image where we can hide that data. So we have this image over here. This is a royalty-free image that I have selected. So I'll click on that and click on open. Now this image loads up in the application. It's a simple highway sort of image, right? And within this area over here, I'll simply write hello from Intellipaat. Now, this is the intended message. Now, this is the secret message that I'm actually trying to send to my recipients. Now, next thing I will do is click on hide text, right? Now we can see it says the text message is now hidden in the image. Now this application is called Quickstego. You can check it out online as well. It's a free to use application, right? And then we'll click on save image. Now we'll click on save, right? And we'll click on something like encrypted image. We click on save, then we click on exit, right? So the next thing I would do is open up the application again and then click on this open image, right? We find the encrypted image option, click on that, and we can see that there is a hidden message attached to it, right? So this is what we essentially get. Uh, we are distributing this application to the intended recipients. They use this application to scan through the image and they see our hidden message, while nobody who does not know about this particular case, that the image is not innocent in nature, will be able to see that message. So this is how image steganography works. So now that we understand steganography in action, let us look at another algorithm. Now this is called the one-time pad, right? Or the one-arm cipher. Now the important thing to know about this particular example is that this is an unbreakable sort of algorithm. Like you generate a one-time sort of key that is uniquely generated for every instance of a new data transfer that you're trying to do, or a new communication instance. And it's called one-time pad because it's only valid once. So it's sort of similar to the OTP that you have, like that you get in your mobile phones when you're trying to log into particular websites, or you're trying to confirm payments. So it's sort of on the same principle, that you get a one-time key that you can enter, which actually helps you go through with your particular transaction, verify your transaction, to so to speak. So say you have a word hello, right? Now, hello can be converted into their respective the letters can be converted into their respective positions on the alphabet. So this is how it would look like if you convert them with respect to the positions they have on the alphabet. So the H is on the 8th position, 5 E on the 5th position. You have two L's, 12, 12, and 15 for the O, right? So you have converted it into that. Now, the next thing that you would do, you would generate a random 5 letter key. So it depends on the length of your string. So if you say if you have a 5 letter, 5 character plain text, you will use a 5 letter key essentially. Now this BXLKD and small can be anything. The only restriction that you need to have over here is that it needs to be of 5 characters, right? So once you've created your randomly generated 5 character key, you will then do the same thing for the key as well. So B is on the second position, X on 24th, L on 12th, K on 11th, so on and so forth. And the next thing that you would do is actually add these two particular numbers, right? So the 8 will be added to 2, 5 with 24, so on and so forth. You get 10, 29, 24, 23, and 19. You can verify this. This is the addition, this is the sum of these two particular individual numbers, right? So when you have that, then what you will do is you'll actually modulo it with 26. You'll find the remainder of these numbers, each of them by 26. So then you get, in that case, you get 10, which means that the number is less than 26, you'll get 10 obviously. When you have a number greater than 26, which is the case for 29, you'll get 3, because 29 is 3 greater than 26. So you'll get 3 for that, and then you'll get 24, 23, and 19, because those numbers are not greater than 26. Once you have done that, you convert them to their respective letters essentially. So if you consider them as positions, this 10, 3, 29, 10, 3, 24, 23, and 19, if you consider them positions on the alphabetical order, convert them back into their respective alphabets. You get JCXWS. Now, this is your Vernum cipher. Like, you've successfully converted it into your cipher, right? So the only thing in this particular case that is needed to be known by the decryption end or the recipient's end is this particular key that you have, which is BXLKD. This is the key that is supposed to be known for that one particular instance of communication between you and the receiver, so that the receiver is successfully able to decrypt your key, right? So this is one-time pad. So JCXWS is your cipher. Now moving on, we have symmetric algorithms. An example of a symmetric or a private key algorithm would be data encryption standard, or DES. Now, this is also used today. There are very few weaknesses attached to it, like weak keys and whatnot, but this is the encryption technique that is widely used today as well. So, it is a symmetric key block cipher published by the National Institute of Standards and Technology, the NIST. So, let us look at how this works. Now, this is a bit complicated, so I'll go through this in a sort of concise manner. This is the diagram of how it looks. So we are going from extremely easy to extremely complex in just a few seconds, right? So say you have plain text. You've converted that plain text into 64-bit blocks, right? So each of these blocks you'll pass through this particular algorithm. So the structure looks something like this. Firstly, the 64-bit plain text blocks is passed through an initial permutation, which means that when the 64-bit plain text block comes into the entire architecture, it is jumbled up. It is jumbled up using a particular permutation table that is there in that part of the algorithm. After that has happened, then you have the 16 rounds. So the DES has traditionally it has 16 rounds. What happens? Uh, each of these rounds gets a unique key, right? So this key is provided by the round key generator, uh, where you actually give a 56-bit cipher key to that round key generator, and based on that 56-bit cipher key, it generates keys for every round, right? So round one gets a key, and based on that key, ciphering happens based on the Feistel cipher technique. In round two, the same thing happens after the data is transferred from round one to round two, and so on and so forth. It is transferred to round 16, and then the key works on round 16 for the ciphering, and then it is passed to the final permutation step. In final permutation, similar to the initial permutation, based on a particular table, the data is jumbled up, and then at the end of it, you get the same amount of data back, which is 64-bit. Now it has been converted into cipher. So the advantages that are associated with DES are each small change in plain text drastically affects the cipher. So this is also called the avalanche effect, essentially, which means that if there is even a small change in the plain text, the cipher changes dramatically, which means it is very difficult to deconstruct the cipher. So it will take a lot of processing power on the hacker's end to be able to deconstruct that data, unless the hacker has any idea about the key. And then each cipher bit depends on several bits of plain text. So this means that each bit that is there in the cipher depends on several bits of the plain text. So even if you change something very small, right, like we discussed earlier on, the cipher bits will be changed by a drastic margin. Then we have an example of an asymmetric example, which is RSA, Rivest, Shamir, and Alderman. Now, RSA is sort of a mathematical operation that happens. It is also widely used today, but it is an asymmetric cryptography algorithm which requires two keys, private and public, obviously, uh, because it is asymmetric in nature. Asymmetric means public key cryptography. So, be with me on this. This is just the algorithm of how this happens. You might be confused by this, but just stick around. You take any two prime numbers, which are P and Q, consider them P and Q. Uh, N is a variable that is the multiplication of P and Q. So you have a variable N, and E is a derived number greater than 1 and less than Q minus 1 and P minus 1, and there should be no common factor between E and Q minus 1, P minus 1. So basically co-prime in nature. So now you have two particular characters, two particular variables called N and E. The public key that will be available to everyone is NE, the combination of NE. This is your public key. Now for the private key is actually calculated, right? So calculate D when ED equals to 1 mod P minus 1 Q minus 1. So E was previously computed, right? The algorithm to calculate D would be to evaluate D for this particular equation. ED equals to 1 mod P minus 1 Q minus 1, right? And then once you've calculated D, the encryption formula would be cipher equals to plain text into E mod n. So this is on the public end side. So anybody is encrypting that data will use this particular algorithm. For anybody who is decrypting that data, they need to know the D value, and that is the private key essentially. The private key is D. They know the private key. So they'll calculate the plain text by multiplying the cipher with d mod n, right? So you can see how the private and public key concepts have been implemented in this particular algorithm, as we can see, right? So you convert the plain text and the cipher into numeric format, and then you apply the mod operation to that with the private and the public keys, and then you essentially get your encryption and decryption. Next up, we have the password storage method. Now, an example of hash functions essentially, where we are actually using hashes in real life, right? So one of the examples for this would be bcrypt. Bcrypt is a hash algorithm. So you create an account on a website, right? And then the website asks you two things, among many things. It may ask you for a lot of other things as well. But the two primary things it asks you for are your username or email and your password, whatever you want to create your password as, right? So these are the two parameters. So whenever you actually create your account in most websites, in most secure websites, your password is converted into an encrypted password by passing through an hash function. So your password is in plain text format, right? And it is passed through a function, a hash function, and it is hashed into an encrypted password. So when it's passed through a function, you get your cipher. This particular cipher or encrypted password is stored in the website user database, right? So whenever you create your social media accounts, your encrypted password is actually stored in the databases of the target social media company, or the company that you're, or the organization where you're creating your account. So naturally, the next thing that you would do is at a later time, you will log into the website, right? So you've created your account, and say one day later, you log into that website. Then upon login, it asks you of two things. It either asks you for your email or your username, and it asks you for your password, right? So what you'll do is essentially enter the password, and what the uh, browser will do for you whenever you type the password, it'll use the algorithm that is intended by that website, and it'll convert your password into plain text there and then, without anybody actually seeing it in the line of communication between the client side and the server side. The password is converted into encrypted format in the user end itself. The password is converted using bcrypt or some other algorithm, and it is converted into the encrypted password. So what is actually passed onto the website is the username and the encrypted password. The encrypted password is then compared to the password present in the user database. So, firstly, the database will look for your username or email. Once it finds that in the primary key section, sort of, and then it'll match the password present in that row, the encrypted password that it has, with the encrypted password that it has just received during your login attempt. If the passwords match, if the encrypted ciphers match, you successfully log into your account, because there is a match in passwords. If you don't have any two-factor authentication available or something, you'll successfully log into your account there and then, right? So the advantages to this: even if an attacker gains access to the user database, right, the attacker can't actually gain access to your account, as the password in the database isn't in plain text format, right? So it's pretty straightforward. If you convert your password into a cipher, which is actually happening at your browser end whenever you're trying to actually enter your username and password and log into your account, it is converted into an encrypted password and then sent over to the server, right? But say a hacker actually hacks into the database of the company or the organization or the website that you have created your account on, and it gets access to the SQL database, say for example, that is present for users. So the SQL database will contain a column called the password, right? So the passwords present in that column will always be encrypted in nature, right? So when the hacker tries to copy that encrypted password and put it into the login tab where your username and passwords are supposed to be entered, we can see in the second image, in the second sort of block over here, that if we pass the encrypted password through that function, we get something entirely different. Now, this something entirely different is then passed on to the website, and it is compared with the already present encrypted password over there, and there is not a match, right? So this essentially tells us that you can convert this password on, if your algorithm is good, essentially the function is good, you can convert the password only one way. You cannot convert the encrypted password back into the password. You can only convert the password into the encrypted password. So this is a very good implementation used in password protection, right? So as you can see, this ensures a lot of security measures, because for the hacker to be able to reverse engineer that password would almost be impossible, and is impossible in most cases. So we've looked at a lot of examples and concepts. So let us see some of these things and how the real world implications of these things work in a practical environment with the cryptography demo with regards to ethical hacking. So currently we have our virtual machine environment open, and I have installed an application called HashCalc. Now this application actually converts text files or any other file into their respective hashes, right? So we have a lot of hashing algorithms available to us. We have MD5, MD4, SHA1, SHA256, 384, 512, so on and so forth, right? So what we can simply do over here is I can go ahead and create a new text file, right? So let us call this plain text, right? And if I open that, I can write some words in it. So hello from Intellipaat, right? So once I have written that, right, I'll save this. So now I have my plain text, which has the message hello from Intellipaat. So in the data browser over here, I'll click on find file, and then the next thing that I would do is go to desktop and find my file, which is over here, plaintext.txt. I'll open that up, and then I'll simply click on calculate, right? So once I have clicked on calculate, we can see that I have my respective hashes available to me. So I have MD5 hash, I have SHA1 hash, I have my RIPE MD160 hash and CRC32 hash, right? So I'll just put it on the left hand side over here, right? And then I'll go ahead and open another browser of hashcalc, right? Now the next thing we would do is go to the plaintext.txt file, and within that I'll make some changes. I'll change the last letter to S, right? So when we do that and put an exclamation mark over there, we've only made one character change to the entire plain text. Mind that, and I'll save this over here. We only made one character change. We've changed the T to S. So we will now close this up, browse again in the desktop, browse to the plain text. We have our plain text txt over here. We click on that, and then we click on calculate, right? So I'll put it over to the left hand side over here so we can do a side by side comparison, right? So we can now see that the MD5s are totally different. The SHA1 is totally different. In the beginning of the first SHA1, we have 4299866, and the next one we have completely different hash. We have for other hash algorithms as well, we have completely different hashes, right? So we can now understand that even changing the plain text slightly can change the hash so much that they are such good viable options for password storage or any other sort of encryption as well. In most cases for password storage, we want algorithms that cannot be decrypted at all. So they are one-way algorithms, and we make sure that they cannot be reconstructed backwards. So let us use another application called Cryptoforge, which actually encrypts files and helps us decrypt them. So, for instance, we have this text file over here, confidential.txt. We open that up, and we can see that there are some details over here, some fake details, Visa credit card number, bank account number, and card PIN. So some people like to keep this information on their computers. It could be risky if you don't actually encrypt those files, so be sure to encrypt them. So I'll close this up, right? So after I've installed Cryptoforge, I get this option to right click on the file and get this encrypt option over here. So I'll click on that. So once I have clicked on that, I can simply enter in a paraphrase, right? So let us enter QWERTY 123 and confirm that and click on OK, right? So now we can see the original file has disappeared over here. We can see we have confidential.txt.cfe, but we don't have confidential.txt anymore. And this is essentially encrypted now. So I'll copy this file and then go to my network folder. I'll go to that. I have two options available. I'll click on Server 2019. This is another virtual machine that is running in the background, right? I'll click on Admin and then enter my Server 2019 password. So once I have done that successfully, I'll go to the users folder, right? And then I can simply go to the public folder and then paste it over here, right? So it's currently in my Server 2019 virtual machine. If I switch back to the Server 2019 virtual machine, I can search for that file. So I have it currently available over here. We can see confidential.txt.cfe. So if I open it with Notepad++ or any other text editor, we can see that we can't actually see anything in this. It's all encrypted, right? We can't actually access the contents of this txt file anymore, right? So the next thing that we would want to do is actually decrypt it. So once I have installed Cryptoforge, I'll simply go ahead and click over here. So once I click on that, it asks me to enter the paraphrase, right? So I'll type in QWERTY 123, click on OK, and we can see the file has been converted into a normal text file again. If I open that, I can see the information that was previously available, right? So that is about it with the hands-on section of how encryption and decryption work in cryptography. So moving on, we are at the end of our cryptography session here at Intellipaat. If you've liked what you've seen, you can apply for one of our courses in the cybersecurity domain where we cover cryptography and other such topics relevant to ethical hacking for our CEH certification training. You can contact our course advisors using the following contact details. They are available 24/7. You can also mail our sales team to inquire about any of our courses or have a live chat with our course advisors on our website, intellipaat.com. So, one another thing, be sure to sign up for our webinar. We post videos like these daily. We host webinars like this daily. So be sure you sign up for that and not miss out on any content from us, and actually have the ability to ask us live doubts if you sign up for the webinars and attend our meetings. Right. So that is about it from Intellipaat. Hope you had a wonderful session. Be sure to like this video and subscribe to this channel if you've liked what you've seen. Thank you and goodbye.